Okay, good morning. This is Professor David J. De Los Reyes. Okay, the date for today is November 20, 2023. The time is around 1:25 a.m. Okay, my topic for this morning will be a continuation of my AC machines, and I am now on lesson number 60. We are running smooth. We are on the concepts of alternators. Okay, let's proceed. The subject matter for this morning will be alternating current machines, lesson number 60. So for those of you who are planning to take up electrical engineering or wanted to study the concepts of AC machines, this is for you guys, okay? So we are now on lesson number 60, excuse me, and the title of the topic will be Example Problem on Alternator Generated Voltage. I will be bringing out an example problem on how to compute for the generated voltage of alternators. Okay, considering the power generation side. Power generation meaning it could be at the dam side where the water turbines are actually operating. They are operated by the live water. So the prime mover of the alternators on the downside is actually a live water. So if we are considering a nuclear power plant, of course the prime mover of the alternator there will be what you call this, a turbine, okay, in which the fuel will be a nuclear energy. And for the wind turbines, that's another story. The prime mover will be the wind. Okay, for the so-called solar panel plantations, of course, there's no rotation over there because the way on how to generate power there is through the sun. But this is all power generation. Okay, let's proceed with the problem. I will try to read the problem. An alternator has the following data. Following data or datas. The total number of slots on the alternator will be 144. It's slots, 144. So this should be a very big alternator. The number of poles is 8. 8 is a little bit on the low side, so we are expecting that the alternator should rotate more or less near 1000. And actually the given RPM is 900 revolutions per minute. Because if this was a 36 pole alternator, okay, it's a very big alternator and we could not accommodate the high speed of that alternator because we got a problem on the so-called machine foundation. So we will just be balancing on the characteristic of the alternator, so we will not concentrate much on the so-called machine foundation. Because on the machine foundation, of course, if it's a big machine, there should be some vibration. And for engineers, okay, they should design a machine foundation in which it will not break up during the operation of the alternator. The total number of turns per coil will be 6, meaning we got one coil consisting of 6 turns, right? And flux per pole, designated by Greek letter P, per pole is 1.8 times 10 to the 6 Maxwells. The unit of flux for alternators is in Maxwells. Maxwell is actually a family name. Okay, I don't know if he was the one who, what do you call this, discover flux. But since the unit of flux actually emanates from his family name, he could be the one who invented or who discovered flux. The coil span will be slots 1 to 16. Later on, we will discuss this is slots 1 to 16. There is a significance of this in the competition. And the winding will be whole coil. Whole coil. Again, we will discuss that one. 3 phase. And the winding connection is star. So if we try to bring out the electrical diagram of the winding of the alternator, if we try to bring out on the circuit board, it will be something like this. It's a star. This is per phase. And actually the problem is asking for the voltage per phase across this. It should be balanced, right? And the voltage between line to line. Because if we could generate voltage, there is a voltage here. We'll just step up this one, going to the transmission line, so we could deliver power to long distances. But actually, where our power actually emanates, it came from the so-called power generation side. Okay, let's try to continue the problem. Calculate the voltage per phase of the alternator, and the voltage between terminals if the connection is a star. So actually, before we could compute for the voltage per phase, there are so many parameters that controls on how the voltage will be generated. Because how do we know there are so many factors? There are so many factors. Because if we would try to bring out the formula on how to compute for the generated voltage per phase, so this formula is actually for designers of alternators, right? It is given by the value 4.44. We derived this one from the previous discussions, times the product of frequency, the flux per pole, times the total number of turns, times the factor 10 to the minus 8. It's just a conversion factor, right? Times the value capital letter K with the subscript P, meaning the pitch factor, times the value capital letter K with the subscript D, meaning the distribution factor. So how many parameters controls the voltage per phase? There are lots. 1, 2, 3, 4, 5. From this equation here, there are 5, but in the computation of K sub P and Q sub P, there are still some parameters which are needed in the computation of this. So more or less 1, 2, 3, 4, 5. It could be 8 or 10 parameters that controls the generated voltage of alternator. Okay, let's start with the solution. The concentration of the solution is actually to compute for all the unknown parameters here before we will substitute it, right? But before we could go here, we start from the start. We'll discuss what is whole coil. To solve this problem, we should know what's the meaning of whole coil. If you try to Google this one, for whole coiled winding, okay, it should be that the number of coils should be equal to the number of slots. That's the meaning of this. Okay? So if we say whole coiled winding, the total number of slots, okay, should be equal to the number of coils. Because we needed the number of coils, okay, in the computation of the generated voltage, because we should have a total number of turns there. But if we do not know the total number of coils, there will be a problem. But according to the given problem, the alternator is whole coil. So if it is whole coil, the number of coils should be equal to the number of slots. So we would like to compute for this one, and since this coil here should be equal to the number of slots for whole coil winding, okay, the value of number of coils should be 144. Why 144? Because the number of slots is 144. Right? So actually, we have computed already for the number of coils from the given condition, whole coil, and since the total number of slots is given, we will just equate that to the number of coils. Okay? Let's try to compute for the coils per phase. Coils per phase. Coils per phase, it is something like this. Right? These are the total number of turns for this phase here, and so with this, and so with this. And for it to rotate equally distributed, the total number of turns here should be equal here, should be equal to here. So if we try to compute for the total number of coils per phase, coils meaning coils is just a wound of wires, right? In which it consisted of actually 6 turns per coil. But we're just computing for the coils per phase. So if we try to compute for the coils per phase, it should be 144 divided by 3. Y phase is 3. For 3 phase, the number of phases will be 3. So this is 3. Right? So the total number of coils per phase will be 48. So in here, there will be 48 coils, there will be 48, and there will be 48. It's balanced. What 48, 48, 48. Okay? What's next? We will compute for the turns per phase. We know the total number of coils per phase, but how many turns per phase? We could compute for that one. Turns per phase will be 48 coils per phase. This one, the one we computed. The unit of this 48 here is actually coils per phase. So this is 48 coils per phase. We will multiply this by the given turns per coil. The given turns per coil is 6 times 6 turns per coil. We must have to place the unit, so if we try to make some calculations, we could visualize what will be the unit of the resulting answer. So coils per phase times turns per coil. This coil here cancel with this. Okay, the operation is multiplication, right? So we could cancel. But just in case this is a plus, you cannot cancel coil and coil. The operation should be multiplication. It's algebra. The operation is multiplication, so we can cancel some value on the numerator and so with the denominator if they are equal. So coil and coil cancels. The resulting unit now will be, this is turns per phase. So turns per phase now will be 288. So in here, there should be 288 turns. In here, there should be 288 turns. And in here, there should be 280 turns. It's balanced. Right? Coils is bigger than turns. So if this is 48, there should be 288, 288, 288. But considering coils, it will be just simply 48, 48 times 48. Okay? Because we multiply 48 by 6 to get 288. So turns per phase is now 288. Okay? We needed this value here later on. So I mark this with the, or I enclose this with the rectangle in blue. Let's try to compute for the frequency. Because if we go back to the formula, we needed the frequency. Okay? And the only factors that controls the frequency is the RPM and the number of poles. That is, RPM is actually 120 F over number of poles. Right? So if we try to compute for frequency, it should be the product of RPM times number of poles over 120. Okay? We are given the number of poles, we are given the RPM, so we could compute for the frequency of the supposed to be alternator. This is 8 poles times 900 over 120, and that will be 620 hertz. Oh, sorry for this one. They should be 60 hertz. 60. They should be 60. Right? So I enclose this one with the rectangle blue marker, because later on when we go to the substitution, we'll just go back here, we could visualize this one immediately. Okay? How about the value of P degree? Why we needed the P degree? P degree, this is the formula on how to compute for the P degree. Pitch factor, rather. because the other parameters needed in the computation of the voltage or phase is the pitch factor. And the parameter which handles or controls the value of the pitch factor is actually P degree. Okay, I place it here. P degree will be 16 over 18 times 180, and this should be equal to 160 degrees. Okay, if we try to visualize that 160 degrees between a north and south, okay, there should be 180 degrees. The electrical distance between a north pole and the south pole in an alternator should be 180 degrees. Okay? But the winding is not actually a pole pitch winding, because according to the given condition, the coil span is only from slots 1 to 16. Okay? So meaning to say, from a north pole and a south pole, there are actually what you call this 18 slots. How do we know there are 18 slots? We will just divide 144 by 8. Okay? What will come out will be the distance between two major poles is actually 18 slots. So the total number of slots accommodated between a north pole and a south pole will be 18. But according to the given condition of the problem, when the windings are actually placed in the slots, okay, the start will be at 1, okay, then it will enter 16. So it will start at 1 number 1, it will go out at 16, but it's not at 18. Because if it's 18, that will be a pole pitch winding already. But according to the problem, it's only 1 over 16. It enters at 1, it comes out at 16. So it enters at 1, it comes out at 16. So if we try to compute the electrical degrees between 1 and 16, okay, it is this. It should be a 16 over 18 times 180. Because if this is 18, P degree will be 183, it's full pitch. But since it's only 1 to 16, this should be 16 over 18 times 180. And P degree is only 160 degrees. This is 160. And this is needed in the computation of the pitch factor. Because pitch factor is actually, am I still on camera? Sine of the quantity P degree over 2. And since we now know P degree, it's 160, right? It enters at 1, it comes out at 16, and that represents 160 electrical degrees. So this is 160 degrees. So this will be 160 over 2, that will be 160 over 2, that will be 80. If you try to bring out the sine of 80 degrees, it's almost 1, 0.9848. Okay, I bracketed this one, or I enclose this one with the blue marker. So later on, when we try to make some substitution, we'll go back to the bracketed thing. Right? What's next? So we now know frequency. The number of poles is given, right? The total number of turns is given. Sorry for that one. Frequency is given, computed already, 60 Hertz. Flux is given. Total number of turns is given. Is the total number of turns given? Oh, it's given. It's 288. Right? So we now know the pitch factor. So the only problem now is the so-called distribution factor. And in the computation of the distribution factor, it's a little bit complicated. It's a trigonometric function. That is, distribution factor is actually the sine of the quantity n times d degree over 2 close quantity over n. Sine of the quantity d degree over 2. So in the computation of the distribution factor, we must have to compute for the value of n. We should know the value of n equal to, and what will be d degree equal to. And what is n? From our previous discussion, small letter n is actually given by the formula. You take the total number of slots, you divide that by the total number of poles, and you divide that again by the total number of phases of the alternator, which is 3. So actually we could compute for small letter n. That will be 144 over 8 over 3, or 144 over 24, and that will be 6. So the value of n here is 6. Okay? So we now know n. The only problem now is d. What is d? What is d degree? D degree is actually the total number of electrical degrees between slots. If this is slot number 1, and this will be slot number 2, okay, the total electrical degrees between slot number 1 and slot number 2, okay, the total electrical degrees, and how do we compute for that one? It will be 180 degrees between North Pole and South, between North and South Pole, there is 180 degrees, right? And there are 18 slots accommodated between North and South. So the total electrical distance between slots will be 180. There are 18 slots, right? Per 180. So it will be 10 degrees. Yeah, it's 10 degrees. There are 18 slots between a North Pole and the South Poles. So if we try to compute the total distance between the North Pole and the South Pole, it should be 180. 18 times 10 will be 180. Or the distance between slots should be 180 divided by 18. And that is actually 10 degrees. Okay, so we now know the value of n. We now know the value of d degree. So by using this formula here, we could now compute for the distribution factor, the one needed here. It's just a matter of substitution now. It will be the sine of quantities n is 6 times 10 degree over 2 close quantity over n, which is 6, sine of d degree over 2, 10 degrees over 2 close quantity. 6 times 10 will be 60 divided by 2, that will be 30, so this is sine of 30 degrees. And 10 degree over 2 will be 5 degrees multiplied by 6, right? Sine of 30 degrees will be 0.5, right? And sine of 5 degrees multiplied by 6 is 0.5229, okay? 0.5 over 0.5229, the distribution factor will be 0.956. Okay, so we now know the value of K sub D. Okay, we are manipulating the equation, right? We are solving the values on how to substitute values here, because without knowing the value of K sub P and K sub T, we could not compute for the voltage per phase. We will multiply this value here by K sub P and K sub T, because this is supposed to be the corrected voltage. There is a variation in the voltage because there is a problem with the pitch factor in the distribution factor. Okay, and this value K sub P and K sub T are almost very near unity, 0.95, 0.94, 0.93, but there is no such thing as K sub P and K sub T to be equal to 1. There is no such thing as like that. Because in reality, there should be a, what they call this, the resulting induced voltage per phase should be a lesser value by this theoretical value here. It should be multiplied by K sub P and K sub T. Okay, substituting values now. So this is now a direct substitution problem after the so long, what they call this, solution on how to bring out the other parameter, right? That's always the case. Because if all the values are given, okay, there will be no challenge, right? So in the computation of all the parameters here, we needed some concepts, okay, in this study of alternator. So substituting values now, it should be 4.44, frequency 60, the flux is given as 1.8 million Maxwells. The total number of turns is 288, where's 288? Right, this is 288 times the factor 10 to the minus 8, a conversion factor from the derived formula. Distribution factor or pitch factor is 0.9848. It's easy to go back, okay? It's enclosed in a blue marker, 0.9848 times the distribution factor. Again, it's enclosed in a blue marker, 0.956. We multiply all these numbers here. 4.44 times 60 times 1.8 times 288 times 0.9848 times 0.956, what will come out will be almost 130,000. And 10 to the 6 times 10 to the minus 8, loss of exponent, right? What do you call this? Is 6 minus 8 it will become 10 to the minus 2. So the resulting multiplier, okay, will be 10 to the minus 2. Loss of exponent, algebra. And 10 to the minus 2, it seems we will divide the value 130,000 by 1 over 100. Right? So this 100 here cancel with this. The operation is multiplication, guys. We could cancel 0 here and 0 here. Okay, so actually we remove 2 zeros here and this is gone. So the voltage per phase will be 1,300 volts. Okay, so each winding of the alternator, okay, should generate 1,300 volts per phase. And the other requirement is, if the connection is a star, what will be the line-to-line voltage? Meaning, line number 1 and line number 2, line number 2, line number 3, or line number 1 and number 3, what will be the voltage? And according to, from the study of star connection, the relationship between the phase voltage and line voltage is actually given by this. Meaning, the line-to-line voltage will be square root of 3 times the voltage per phase. Square root of 3 times 1,300, it is 52 volts. The one we did on the vector diagram, right? It is something like this, right? This is the voltage line to line, and this is the voltage per phase. There is an angle of difference here. Because we will add the voltage per phase vectorially to get the line-to-line voltage. And the relationship for a star connection is given by this one. That is voltage line-to-line will be square root of 3 times the voltage per phase. Okay, that's it, guys. So that's the way how to compute the generated voltage of an alternator considering distribution factor and pitch factor. Okay, good morning from Los Angeles. This is Professor David Generatedvoltage.